So let's look at where we started with our previous lesson with the disk method. Okay, and let's review a few of these for right now. Okay, and it says we want to find the volume of the solid generated by revolving the region bounded by the graphs of the equations about the given lines. Okay, now what you looked at yesterday was revolving something around the x-axis. Okay, so here's our function, radical x. We're going to revolve it around the x-axis, and it's going to create this kind of bowl-looking thing. All right, so something kind of like this. We try to draw in 3D. Okay. All right, you can kind of see what this would look like.
A cylinder has a constant radius, right?
Yeah, a cylinder has a constant radius. We're creating something kind of based off of the idea of the cylinder, okay? So remember our formula for volume is pi times the integral from a to b of whatever that function is squared dx, okay? Because we're dealing with pi r squared dx because it's the volume of a cylinder, but we just made an infinite number of cylinders and added them all up, okay?
Like the radius is the function.
The radius is the function. So in this case, we have pi times the integral from 0 to 4. Okay, 0 to 4. So we are given x equals 4 as one of the boundaries. And then we have radical x that we are going to square. And then we integrate. Okay, so square root of x squared cancels out. We have pi times the integral of x is x squared over 2, evaluated from 0 to 4.
One question. The reason why we're not doing the n to the power divided by 2, all those mathematical stuff, is because we can use the fundamental theorem of problems?
Yeah.
Okay.
Yeah. And the reason why we went back and looked at that in our previous lesson was just to show you how this whole function is developed using those disks. Okay? So now, if we plug in 4 squared is 16 divided by 2 is 8. If I plug in a 0, I get 0. So this whole thing has a volume of 8 pi, and then whatever the units are cubed. Okay, cubic units, because we're dealing with volume.
Is it like considered the basic problem?
That's our basic type of problem, yes. Okay, now we will address other things here as well. We can find this though. Let's deal with one other one of these, and then we will address the ones that revolve around other lines later on. Okay. But part B, if I'm revolving this around the y-axis, what's the first thing though that has to be true? If I'm revolving it around the y-axis,
it's continuous.
Well, it does have to be continuous, and it is continuous here. Yes.
Isn't the last unit should be cubed? Is it small?
Cubed, yeah. Sorry.
It has to be a function.
Well, it doesn't actually have to be a function. Remember, we looked at ones that were not functions, but the reason why they don't have to be functions is because we rewrite them as x equals something with a y as opposed to y equals something with an x, right? So if I'm rewriting this function, I'm going to rewrite this as x equals what?
Y squared.
Y squared. Now, I do still need the same domain and range, okay? So the domain for the previous one was that x had to be greater than or equal to 0. So on this one, y has to be greater than or equal to 0. Okay?
Why? What if it's squared? Or even if it's squared?
Yes.
Okay.
In order to wrap the same thing, in order to have the same graph here. Okay?
But
In this case, what we're doing is we're revolving it around this way. It's going to look like this.
So now you have a vertical?
It's like a big cone, or like a funnel you pour stuff into and it funnels through. It looks like a big funnel.
Wait, so
all right.
In order to revolve over the y-axis, we just like have to do the inverse function.
Well, it's not an inverse function. We're not switching the x and y and then solving. All we're doing is we're solving for x, because in this case here we're gonna find volume as pi times the integral from a to b of, and now the radius is going to be a function of y. Okay, and we're going to integrate with respect to y.
Wait, you should get the same answer, right?
We should end up getting, well, no, because we have two different objects now. You see that?
They have the same equation, right? Like they represent the same thing.
But we're not revolving it around the same thing. Here we ended up with this bowl-shaped thing. Now we're ending up with this funnel-shaped thing. So they're two different objects. The volumes are not going to be the same.
All right.
Or if they are, it's just by chance. Okay? So in this case here, now we have v equals pi times the integral from what to what?
Y squared.
From
From
4 to minus 4?
From 0
What are our y's going to?
0 to
Oh.
4.
0 to...
Infinity.
No.
0 to 4.
0 to 2. Okay? 0 to 2. Alright, so integral from 0 to 2 of y squared dy. Okay?
You're going to 2 because it's squared.
No, we go to 2 because we're dealing with y's here, not x's. Okay? This point here was the point 4, 2. Right? So on the y-axis, we're only going up to the value of 2. Okay? So we have y to the 4th. We integrate that. It's pi times y to the 5th over 5, evaluated from 0 to 2. So pi times 2 to the 5th, 32 over 5 minus 0. Okay, so we just have 32 pi over 5. Or if you want, that would be a 6.4 pi.
Oh, so that was worse.
But again, that would be units cubed. Okay? So this is a little smaller than the original one was, but it's a totally different shape. So, okay? All right. We'll deal with the other two types later on, but that's all for now. What we want to look at today actually is what's known as the washer method. Okay? Now, if you've never built stuff before, this may not make sense, okay? But how many of you are familiar with nuts and bolts? You've built some stuff, and usually the nut has a hexagonal head, okay? And then, well, there's a good bolt, okay? And the bolt will screw onto the nut, but a lot of times what will happen is you're doing this with wood or something, and you don't want there's a lot of pressure, you don't want it to rip through the wood, so you put this circular washer in between the nut and the bolt, and it has a hole in it, okay? And then, you know, here's the bolt. Okay, that gets screwed in through there. All right, but the washer helps distribute the pressure so it doesn't rip through the wood. Okay, That's what we're talking about when we're talking about a washer method, not like a clothes washer. All right? The washer method is just like the disc method, except the discs all have holes cut in them. Okay? That's why they look like washers. All right?
How would you cut a hole in it?
Well, let's say that we wanted something, well, maybe a washer, okay? Or this bowl-shaped thing up here, let's say we want it to be a certain thickness, but we want it to be hollow so it'll actually hold stuff. Before, what we were looking at with the disc method was called a solid of revolution. It was solid. Now, what we're going to deal with is something that actually has a hole cut out of it, and that hole is maybe what it would contain, but what we want to find is what would the volume of the object be, and you could use that to, say, figure out how much material you would need to make it. You know, how much steel is it going to take to make this thing, or how much plastic are we going to have to use to make this bowl or whatever. Okay? You need the volume of that.
But can you use the volume of the other one as well?
What do you mean?
Can you use the volume of the other one on top for the solid to figure out how much material you need as well?
You are, and actually that's where this formula kind of starts with. It starts with the volume of the solid. Okay? Now notice what we've got here. We've got, because we're cutting a hole out of this, we're dealing with an outer radius, which is the volume or the radius of the solid object. And then we have this inner radius, and that's the radius of the hole. Okay?
The whole thing minus the area of the small?
Yeah.
Okay.
And that's exactly what this is, and then we clean it up again to make a prettier formula. Okay? So we have, using our volume of a solid with the disc method, the volume of the entire thing, we'll call volume of the solid, is pi times the integral from a to b of that capital R of x squared dx. The volume of the whole, I'm using that inner radius, so pi times the integral from a to b of the inner radius squared dx. And then, like you said, we take this solid and we subtract the whole, and we get the volume of just the part that we want. Okay, and that's where we get this formula here.
Is the function different, like the R capital and R not capital? Like these are different functions?
Yes, guys. The outer function and the inner function, the outer radius and the inner radius are different functions. Okay, and this is kind of cool because we don't have to have the same shape on the outside as we do on the inside. Okay, we could have a bowl, say something that looks like this, a normal bowl on the outside. Okay, but the inside may kind of be like a funnel. Okay?
Is that bowl really like that?
What's that?
Is that a bowl really like that?
Wait,
You could make one like that.
wait,
No, you couldn't.
Why not?
That's so hard to make like an angle, like.
Well, that's the beauty of the math here, is that if you can get formulas and equations for those different shapes and then spin them around, it's actually very easy to make these things. Okay?
The thing is, how do you come up with the formula though?
Well, that's where you gotta, all that stuff you did in algebra and we've been doing through calculus and stuff to write equations for things. Okay? That's where all that comes from. Okay? Or this is what all this could be used for. All right? All right, so let's look at an example of this here. A couple examples. Find the volume of the solid generated by revolving the region bounded by the graphs of the equations about the given lines. Okay? So we're going to revolve the region bounded by the graphs of the equations about the given lines. So, first of all, what do we mean by bounded by the graphs? This is, guys, a term that all of you need to make sure you understand.
Between them.
Like
Between them, enclosed. So what am I looking for? Intersection points. Okay? I've got these two, and here's where a sketch of these curves might be helpful. Okay? I've got my y equals x squared. And I've got an x-axis, okay? I've got the x-axis, or, sorry, the 4x minus x squared. So that has zeros at 0 and at 4.
2. No, 4. 4, sure.
Okay? And it's a parabola opening downward, so it should look like this. Alright, so by the way, I already know what one of the intercepts is, right?
Yeah, 0.
It's 0, okay? One of those intersections is at 0. If I find the others, x squared equals 4x minus x squared. I've got a 2x squared minus 4x equals 0. I take out a 2x, and I have an x minus 2 left. So my other one is going to be at 2, okay? So right here, oh, I actually drew it right. That's our point 2, 4. Okay?
It's subconscious.
Yeah, just subconsciously did it. Alright, so now if I'm revolving this area around the x-axis, one of the things you have to make sure about is that you are revolving it, keeping in mind which one is above and which one is below. Okay, which would be our outer radius and which will be the inner radius. Alright, so if I'm revolving around the x-axis, I have the outer radius, which is going to be that 4x minus x squared. So 4x minus x squared is squared. Minus the inner radius is just that y equals x squared. So I have the x squared squared.
Wait, when you revolve around the x-axis, it's vertical? Like it's vertical?
Yeah, it's going to end up, actually, that shape I just drew you where it looked like a normal bowl on the outside and it was a funnel on the inside, that's exactly what this is going to look like. Because look, the outside is going to look like this nice normal bowl, but the inside is going to have this shape, like a funnel.
How do I know which is upper and which is lower?
You just got to look at your line that you're revolving it around and see which one is further away. Okay?
So you're getting
Don't necessarily think upper and lower, think outer and inner. Okay? Think outer and inner. So guys, let me just finish this here and we might answer your question. So what are we integrating? What interval are we integrating over here?
0.
From 0 to 2. Alright? So because those were our intersection points from 0 to 2. So of course we're going to need to FOIL, do some simplifying before we integrate. Okay, but you guys know how to handle this. I'll just do it quickly. We've got a 16x squared minus 8x cubed, and we got a x to the 4th minus an x to the 4th, which is 0. So it's just that dx. Okay?
So, Mr. Dixon, when you, if you couldn't graph the equations, can you still just do what we used to do about plugging in a point during that?
Yeah. Oh, yeah. And here's the thing. Same thing that happened before. If you did it and you got a negative value, you just realize, oh, I did it backwards. So you just make it positive. Okay? Don't redo everything. So here we've got 16x cubed over 3 minus 8x to the 4th over 4, which is going to be a 2x to the 4th, evaluated from 0 to 2. When you plug in 0, it's all 0, so I just have to plug in the 2. And I get pi times 8 times 16 is 128 over 3. So that's 42 2/3 minus 2 times x to the 4th is 32. So this is just 10 2/3 pi.
How did you follow this?
All right, now earlier in the warm-up we skipped the couple that revolved around other lines. But I want to address that here, okay? We can revolve this around the line y equals 6, okay? Now this is kind of an odd thing to do, all right? But the reality is we can revolve this however we want, okay? So 1, 2, 3, 4, 5, 6. So here's this line, y equals 6. Okay? Now, what does our formula revolve this thing around? The x-axis.
So it doesn't matter.
So, how could I get it to revolve around the line y equals 6 instead?
Add a plus 6 to
You're on the right track. Instead of adding a plus 6, subtract.
Why?
Let's shift this entire graph down 6 units. Okay?
Okay.
Because if I want to revolve this around y equals 6, you know, up here, it's going to look something like this. And the outside is going to be curved like this. The inside will be curved like this. Notice what you revolve it around changes the entire look of what this thing is. This almost looks like a... I don't know what that looks like. Because it's like bulging out on the outside, but it's bulging in on the inside.
It looks like a fly.
I don't know.
If you're gonna look at it, that's
So, but regardless, here's what we've got to do with it, okay? What we're going to do is we're going to shift it down. How do I make y equals 6 into the x-axis? I do y equals 6 minus 6. So if I do the same thing with my other two functions, they'll both be intersecting at this point 0, negative 6. And instead of 2, 4, it'll intersect at 2, negative 2.
But why do we shift it down and not up?
Well, because our formula is for revolving stuff around the x-axis. So if we make our function, or our line that we want to revolve it around into the x-axis, all we have to do is adjust the other two functions in the same way. Okay? So, that initial one, this one here, that was opening down, this was the 4x minus x squared. So guess what? I just do minus 6 at the end. And this, that was just y equals x squared, I'm now going to make it into x squared minus 6. Okay? And now I have this, and everything's been shifted down 6 units, so I can use the formula we've got. Okay? So, now, be careful here with this one because we have an outer radius and an inner radius. In this case, the outer radius is going to be the one further away from the x-axis, so that's that x squared minus 6. So I'm going to be doing the integral, pi times the integral. It's still going to go from 0 to 2, but now I've got an x squared minus 6 squared minus the inner radius is going to be 4x minus x squared minus 6 squared dx.
No, because that one is
Wait,
further away.
why does it change which function's on top?
Well, we're not talking about what's on top. Remember, we're talking about an outer radius and an inner radius here.
Okay.
So, remember, what we're revolving it around is the x-axis here. So, this one that happens to be on the bottom here is going to make our outer radius when I revolve it around. And this is going to make the inside of whatever this object is after we revolve it around. I know it's hard to see this stuff in 3D, but...
Wait, when you did it above the x-axis, wasn't everything opposite? No?
Yeah, because we were revolving it around something that was below it. Here we're revolving it around something that's above it. So you got to think outer and inner, not top and bottom.
So how do you know which one is in here?
Which one is closer to the line that you're revolving it around, and which one is further away?
So closer means...
Okay, so at this point, we've got a lot of foiling to do, and it's a pretty basic function at this point to integrate. It's just kind of messy because we got a lot of foiling to do.
Sure.
So for sake of time, I'm not going to finish off the whole thing, but you see how this would be set up. Once it's set up, we're just doing stuff we've been doing for months.
Or
Okay?
plug it into the calculator, which is also an option.
Yes, and if you have a calculator available, do not ever do that by hand if it's calculator active. Okay? Do not waste your time doing that by hand if it's calculator active. Alright? So, that one was a bit complicated because it was area between two curves, then revolved around. Let's take kind of a step back mentally a little bit and look at one where we're just revolving it around the line x equals 6. Okay? So let's sketch this and see what we're dealing with. We have the line y equals 6 minus x. So 1, 2, 3, 4, 5, 6. 6 minus x has a slope of -1, so it's going to be here. We have the lines y equals 0, which is our x-axis, y equals 4, which is there, x equals 0, which is here. Okay? So notice the region that we're dealing with. We're dealing with this like trapezoid looking thing right here. And we're going to revolve this around the line x equals 6. Now check this out. This is going to be kind of a cool looking thing. So here's our line x equals 6. Alright? Now, for one thing, we're revolving it around this way, so what are we going to be integrating with respect to? Y. Okay? So, this thing in the end is going to end up looking like this. It's going to look like a cylinder that has a cone cut out of the middle of it. Alright? Yeah, it's kind of a cool looking thing. It's hard to picture. Okay? Can you see it here?
I have good imagination.
Yeah.
No, I see that.
You see it now?
Yeah.
It's another bowl.
It's like a bowl, except the inside is just a cone. Alright? So that's kind of a wild looking thing here, but okay, so first of all, we need to integrate this with respect to y. So I'm going to rewrite my function as x
negative y plus 6.
negative y plus 6. Okay? X equals negative y plus 6. Now, I'm also going to be integrating from what to what?
From 0 to 4.
From 0 to 4, yeah, from 0 to 4 because I'm going along the y-axis. Here's the thing though, I'm not revolving this around the y-axis, I'm revolving it around the line x equals 6. So what do I need to do?
Oh, you have to move it to the left.
I need to move it over. I need to move it over to the left, okay? So I need to subtract 6. Okay, think about this is kind of the easy thing to whoops.
Wait, but why do we need to move it over?
Because you got to revolve a line x equals 6.
Think about it like this. I need to revolve it around the y-axis, which means I need to subtract 6 to get it over here to be x equals 0, right?
Yeah.
So that means I need to subtract 6 here as well.
But why though? Like why do you need to subtract if you're forcing the other one to be y-axis? You know?
Because our formula is designed to revolve it around the y-axis. If we're not revolving it around the y-axis, we need to shift everything over so we are revolving it around the y-axis.
Okay.
Okay? So what we end up with here, we actually are ending up with everything shifted over. And let me redraw this the way that it is after we've shifted it over. Now we're revolving it around the y-axis. It's the line x equals negative y. Okay, here is y equals 4. Okay, and now it's over here, it's hitting at the point negative 6, 0, and when originally it was hitting over at 0, 0. Okay, still going to be the same shape. We've just shifted it over so our formula will work now.
Wait, so we're doing it so like the shape stays the same, but we have to do it from the center.
Yeah.
Yeah.
And if it's like, if the shift is not only like in x or y axis, if it's like first.
Well, it won't be both.
Yeah.
Okay, guys, good question here. We're not going to have anything shift that we're going to have to shift horizontally and vertically because you're only revolving it around the x-axis or the y-axis. You're not going to revolve it around both. Okay?
Could you?
So you would only have to shift it once. All right? So now that we have this, we have our revised. Here's x equals negative y. We're going from 0 to 4. So now we're integrating, okay? We have to consider the area between this curve, which is x equals negative 6, and our line. Do you see that? So now we do have an area between the curves, okay? It's this area here. So the outer shell of this is going to be which function? Or which equation?
Five, R1.
Minus 6. X equals negative 6. That's going to be our outer shell. Okay? Because that's this side over here. Okay? So we have that vertical side right there. Minus the negative y squared, because that's going to make the inside of this 3D object. Okay?
Oh, okay.
Why is it y squared?
Wait, what's the horizontal thing?
Because it's the inner radius squared.
Oh, right. Yeah,
Okay.
Yeah, true.
And what about the y equals 4? How do you do that?
Well, the y equals 4 is where we got this from, right here. We're going from 0 to 4.
Oh, okay.
Okay? So just to finish this out, v is pi times the integral from 0 to 4 of 36 minus y squared dy. We have a 36y minus y cubed over 3 evaluated from 0 to 4. Okay, when we plug in 0, it's all gone. So pi times 36 times 4 is 144. Y cubed, 4 cubed is 64, divided by 3 is 21. And 21, 64 divided by 3 is...
Blanked out?
21
21 point, yeah.
and 1/3?
Yes.
Yeah, jeez. 21 and 1/3. Okay. So we now have 142 and 2/3 pi cubic units. Okay? Okay.
So when we're shifting it to the left, to match the axis, the reason why it's negative y plus 6 minus 6.
Okay. Let's do one more for practice here. Using an exponential. Here we have an exponential decay function. All right, we're gonna revolve this around the x-axis. Okay, so let's sketch it first. You all know what the exponential decay function looks like. It comes down and it hits at 0, 1. Okay. Or I should say, yeah, 0, 1. Okay. And we want to go from y equals 0, x equals 0, and x equals 1. So here's the point 1 over e. Okay? So the object that we're dealing with is going to look like this. Okay? So there's the profile, if you will. And then when we revolve that around, it's going to kind of look like a little volcano or something.
Or a skirt.
But this one actually will be, yeah, or a skirt. This one actually will be solid. Okay?
Because we're making it solid?
Yeah, just with the bounds that they gave us, that's what we got. We got something solid. So now we have, we're going to be doing the volume is pi times the integral from 0 to 1 of our function, e to the negative x. Okay? What's the integral of e to the negative x?
E to the negative x. No, negative e to the
Negative e to the negative x, okay? So this, I'm going to pull the negative out. So negative pi times e to the negative x.
Why is it not squared?
Oh, shoot, yeah, thank you. Got carried away. We got to square this, right? Thank you. All right, so that changes things a little. 0 to 1, e to the negative 2x dx. So now we have a little bit more work to do with our u substitution.
just negative 2 e to the
So we have negative 2 dx. So we need a negative 1/2 out here, right?
Bless you.
right.
Yeah.
So now our volume is negative 1/2 pi e to the negative 2x evaluated from 0 to 1. By the way, here's a good example. Don't just always assume that when you plug in 0 it equals 0.
It equals 1.
Because in this case it equals 1. So negative 1/2 pi times, if I plug in a 1, I have e to the negative 2. And if I plug in a 0, I get 1 Okay? So,
Don't we just stop there?
Looks pretty good to me.
we've got a negative 1 over, a negative 1 pi over 2e squared plus 1/2 pi. Okay? And by the way, that should be positive, right?
Yeah, hopefully.
Yeah.
Okay. It is positive because we had a negative on the outside, and e to the negative 2 power is a fraction. So if I subtract 1, it's going to be less than 0, so negative and negative makes a positive. Okay? So this many units cubed will be our answer.
So what's the derivative of the integral of something that's not a like another number to the power of x?
Remember, if it's like 2 to the x, it would be 2 to the x over ln of 2.
Oh, okay.
Yeah.
But
All right.
In this case, we're doing ln of p, but ln of p is dividing by 1. So
Yeah.
it's really-
Yeah.